2D sprites can attain the atmosphere, shape, and dynamic lighting that 3D shading offers through the use of secondary textures. This video is a comprehensive guide on how to create and use texture maps to enhance the look of your 2D game. At the link in the description, we have a small package of shaders for you with the special effects we'll be covering in the FAQ section at the end of the video. But before that, we'll start with an explanation of what normal maps and mask maps are, and then we'll cover how to set them up in Unity. From there, we'll touch on the various workflows and techniques to create them, whether the art in your game is drawn, painted, or created from 3D models. Texture maps contain information used to define the appearance and properties of a surface. Normal maps are a specific kind of texture map that encodes surface detail information. The color values of each pixel represent the direction that the corresponding pixel is facing on the main texture. While our focus is 2D, the 3D context is helpful here. Traditionally, normal maps are used to replace geometric details with texture data. Here I have a model of a clay figurine from the Jomon period of ancient Japan. Since it was created with photogrammetry using hundreds of photos, the mesh has a lot of detail, 500,000 triangles. Modern tools aside, this is generally considered not a game-ready mesh, and it's certainly not suitable for animation rigging. I've decimated the mesh to around 7,000 triangles. A normal map can be created through a process called baking, where the difference in surface normals is calculated between the original high-poly mesh and my low-poly one. The surface details are then added back to the low-poly mesh with the normal map. Even if you're a dedicated 2D artist and you're never going to 3D model, I think you'll appreciate how amazing normal maps work given how close these two models are. So why would we do this? What makes a texture better than a bunch of polygons? In Unity now, I have 10 figurines with 500,000 triangles each. Each one is as big as the entire terminal scene. That has us at about 30 frames per second. We'll get better performance with the low poly model and normal maps. With the 7K figurines, we're getting around 60 to 80 frames per second. Textures are much more efficient to render because GPUs are very good at parallel per pixel operations and have a fast memory cache dedicated to textures. For 2D graphics, normal maps can give the illusion of depth, shape, and dynamic lighting to what otherwise would be a flat image. You're already familiar with what the normal map colors represent from the axes of the Unity gizmos. Red indicates how much the surface is facing the right, the x-axis. Green shows how much the surface is facing up. And blue represents how much the surface faces forward, the z-axis. Let's take a look at exactly how normal vectors are mapped to colors, the RGB values. That way you'll understand why it's mostly purpley but has these bright colors on the edges. Surfaces, by definition, face outward one way or another, and because the z-forward value of a normal vector is never less than 0, every pixel of a normal map is at least halfway blue or above. When facing down and or to the left, the x and y of normal vectors go into negative values. And since there's no such thing as negative color values, the corresponding red and green values are remapped to go from halfway down to 0. Therefore, normal maps look purpley because there's a strong blue element to most of the data, except on areas of the edges, especially on the top and right, where the green and red values surpass the blue. Let's take a quick look at a few specific colors on a normal map painting palette. A smooth flat surface is equal parts red and green, and the maximum value for blue. The hexadecimal can be handy to memorize, 8080FF. The pure blue on the bottom left doesn't mean that the surface is extra forward. It means that the surface is not facing to the right, so there's very little red, it's not facing upward, so there's very little green, and blue is most all that's left. As the surface faces less forward, the shade of blue gets darker, which makes sense considering that 000 is black. You'll notice that there is a gray or desaturated blue spot in the middle upper right because the RGB values will all be similar. Additive RGB color mixing is different from mixing color pigments. On my desk, I have a red light shining on a white piece of paper. Now watch what color we get when I turn on a green light. On the left of the page, where the colors are equal strength, our eyes perceive the color yellow. With red, green, and blue lights like those in our monitors, we can manipulate the 3 kinds of cones in our eyes to interpret all the other colors. As we just saw, we get yellow from red and green light, magenta from red and blue light, and cyan from green and blue light. Alright, so that's a bit to explain, but now you know why we get all of these colors from mapping normal vectors to RGB values. Mask maps in this lit sprite context use a color channel like the red channel to define specific areas that will receive special light effects like rim lighting or highlighting. Here I have a sprite created from a 3D model. This is just a flat base color because the secondary textures will provide the shape and shading details. I'll show you how to make secondary textures in the next chapter, but the setup in Unity is the same regardless of the process you took to get here. In addition to your sprite, you'll have a mask texture if you're using one, and a normal map. Select your normal map, and in the import settings, in texture type, set it to be of type normal map. And click apply. In the inspector import settings for the texture, set it as a sprite, and then go into the sprite editor. In the sprite editor, in the top left drop down, go to secondary textures, and then click on the plus to add the textures you're going to use. I have a mask map, so I'm adding 2. The first name, make normal map. In the second, make mask text. And then find your normal map for the sprite, and the mask texture for the sprite. And then the only thing left to do is click apply. And there we go. Now our couch has shape and shading from the normal map, as well as highlights from the mask map. Let's do a quick walkthrough of the lighting setup. I'll turn off all the lights to start with a blank slate. First, a global 2D light to have some flat lighting everywhere. In this scene, we don't want things to be completely black, so this lays the foundation. Then I'll turn on the windows, which include an HDR shader for an emissive glow. We'll walk through a shader similar to this at the end of the video. I'm turning these on now because lighting should generally be grounded to where it's coming from in the environment. On that note, the key light, or main light, is a large spotlight 2D that falls off to the front of the room. This light has normal maps enabled. At a distance of 0, the light only affects areas that face the light. Areas facing away from the light are unaffected. If I bring the distance up, it's like the light is moving forward to the viewer on the z-axis. And the shadowed or opposite-facing areas are more affected. The light is then softer or more diffuse. A setting of 0 then most defines the surface, and it makes sense for an interior where the light is coming from specific windows. In environmental psychology, this room is called a type of refuge space. So don't just think of shadows as scary because being in shaded areas makes us feel cozy and safe. Next up we have the window lighting, and these lights use the additive with mask red channel blend style. The lights also use normal maps with a bit of distance, which you can just move around until the sprites catch the light in a pleasing way. Now watch the curtains as I turn off the normal maps. The whole mask texture is lit. With normal maps enabled, only the areas of the mask texture that face the light are affected. If your lighting is non-environmental, you may want to use separate lights for normal maps and mask maps, as in the case of a highlighting effect or a general rim light effect in a flat puzzle style game. And then one final touch, a sprite light 2D for the sunlight coming through the window. These have the multiply with mask blend style. Watch the barrel here. When I turn it off, without the multiply with mask, we get some light where it shouldn't be. Sprite lights can also have normal maps enabled. You can see a subtle change to the floorboards when I turn this on. But in this case, the difference is pretty small, and I think we want more of that warm glow than we want definition from the floorboards. There are several different workflows to make secondary textures, so first let's look at workflows for 2D art. Let's say you have some 2D art you've created. Wouldn't it be nice to just click a button and get a normal map for this? Well, there's several programs you can try to give this a shot. I'm using a free open source program called Materialize, but all these programs work pretty similarly. First, import the base color, and then from here, I'll make a height map. I'll play with the parameters until I think I get something that is going to make a good normal map from this. And then I create a normal map from the height map. Alright, and that looks good because this art is a very ideal scenario in that there's nice gradient shading that looks like it's lit from the front. In Unity, it looks great. And like I said, there's a bunch of tools that do something similar to this. Here's a web-based tool that's been around for years, Normal Map Online, and it functions in a similar way. For example, they provide a way for you to invert the channels if they're wrong, like how the red here needs to be on the right side. So this is a really fast way to make a normal map, but it's not going to work a lot of the time. Here's an example of how it doesn't work. The base color values don't translate to height, like how we're getting these weird bumps from the highlighting and shading of this watering can. That said, using a height map in your normal creation process can be useful. Let's say I want to quickly add some shape to a simple icon like this star. In a vector graphics program, you can create gradients to set up height information. In Illustrator, I can create a 3D effect by inflating the shape and then changing the lighting to be diffuse from the front. And then in Unity, I can import this texture as a normal map, converting the grayscale from the image. And for this, I'll bring the bumpiness down and make the filtering be smooth. Then click Apply, and now our star has some shape. You could also try layer styles in Photoshop or GIMP, like trying a bevel, or an inner glow with black for the color. Most of you will end up painting your secondary textures, but as long as we're talking height to normal map workflows, this is Substance Designer, which is a node-based generative art and material creation program. Here I'm running a star shape node into a bevel node, which has a normal map output. There are tons of adjustments we can make to the normal map generation, and we can see what we're doing on a lit material in the 3D viewer. The program is for seamless 3D material creation, but if you're more of a vector art person than a painter, and you love tinkering with parameters, then this may be worth checking out. Painting the normals gives you the most control and best result, but of course it requires a bit more time and attention, in a way because it's like sculpting the surface of your artwork. If the art or prop is angular, you can fill the colors for where the surface faces. After masking out the image from the background and moving the mask to the normal painted layer, I'll make the background the front-facing color, and then draw shapes with a selection tool, filling in colors from a normal map palette. Of course, this is really easy if you have your art separated in layers where you can just duplicate and then fill in your pieces. If you use Photoshop, the color fill shortcut is Alt Backspace, but I like to map this to F3 because it's much easier to have one hand on the function keys when you're using a drawing monitor. Even though this rock from Happy Harvest is flat, I can add more shape detail to the artwork not present in the base map. While you can use any painting program to paint the normals through sampling the colors, some tools like Sprite Illuminator are dedicated to painting normal maps. It's really helpful to see the lighting of your surface as you're painting it. There are a few helpful features to this program, like how it default masks the image apart from the background, and you can have the light automatically rotate around the sprite as you're painting. Another great method, which is in our ebook, 2D Game Art, Animation, and Lighting for Artists, is to paint your art lit from different directions in the separate color channels. Then you get your normal map from combining the RGB channels. I'll demonstrate one way to do this. Start by masking your art, and then fill your painting layer with either the neutral normal map color or a flat gray 128, 128, 128. Then bring down the opacity to see the art we're painting on top of. In the red channel, paint your art lit from the right. We're painting in grayscale, so if we paint black, we're actually removing red, like on the left side, which would be shaded if it's lit from the right. In the green channel, paint your art from the top, with black shading on the bottom. And then in the blue, paint things lit from the front. Since I started with blue at the midpoint, I'm just going to paint everything white, and then have half gray on the edges. Alright, I'm just doing this really fast to demonstrate. Let's take a look at it. Alright, so this gives a really nice result. It does take time, but many artists prefer it to painting with a normal color palette. Here's the finished normal map from the Dragon Crashers project. Let's take a look at the channels. Red lit from the side. We can see gradient fills being used to good effect here. Let's check out the green channel lit from the top, and the blue channel lit from the front. And at this point, you know exactly why the blue channel never goes below half gray. If you're rendering out images of 3D models and importing them as sprites in Unity, creating normal maps is fast because the normal information is already there. In Blender, a quick way to make normal maps is to use the matcap shading, and then set the viewport display to the front-facing color. In the Render Properties tab, turn off transparency. And then in Color Management, switch the view transform to standard if it isn't standard already. Then go up to View and select Viewport Render Image. And then in the image dropdown, select Save As, and you can save this image anywhere, like in your Unity project. The matcap method works great much of the time, but the most accurate method is to create a normal material shader. This works especially well for more complicated scenarios, like when you have objects in front of other objects. The texture coordinate node generates coordinates that can be used in various ways. In this case, we're using the normal vectors of the object surface and object space. The vector transform node allows us to transform vectors between different coordinate spaces. And here we're transforming the normal vectors from object space to camera space so that the normal map is oriented relative to the camera's perspective. The mapping node lets us adjust the coordinates before they are used by the shader. The original normal vectors of -1 to 1 for the x and y are remapped to 0 to 1 for conversion to color. Z is 0 to 1 and is remapped to 0.5 to 1, but it's flipped so that the forward direction faces the camera. Now the values here are confusing because the texture type does inverse transformations, so let's take a look at what's happening here with this mapping on a sphere. Here I'm separating the x, y, and z and using a combine color node to put them back together. Let's look at the x values and undo the mapping. There you can see how the black is negative values, 0 is in the middle, and 1 is on the right. -1 then in the mapping moves everything to the left as you'd move a texture or an object, but it's actually adding 1 to the values, as we can see in how instead of -1 to 1, we have 0 to 1 in the middle, and then 2 on the right. And I've turned on bloom to show you how the value is above 1. When we scale our texture mapping by 2, we're actually dividing the values, so now we have a range of 0 to 1. While we're here, let's take a look at the gamma correction the gamma node is doing. If we skip over this node and look at the linear values, where would you say 50% gray is on this sphere? It wouldn't be in the center because that looks too bright. Middle gray to our eyes is somewhere here, like 20% in the gradient. Our eyes are tuned to darkness because that's how our ancestors survived the night. We see variations in darker shades more clearly than brighter areas. So while our normal data is interpreted linearly, we want to see the colors in a corrected way. sRGB gamma encoding basically puts more bits in darker shades and less in brighter shades to make the most of the data available. Normal maps do need sRGB gamma correction because we're just not going to see the difference in colors in the bright linear color space. Back to the sofa. To render this out, first go to the World tab and set the background color to the hex 8080FF for the neutral forward-facing color, and then press F12 to render the image from the camera, and Image Save As to save it in your project. Mask maps can be created by setting up a simple custom shader. Start with a basic material, and in the shader editor, add a shader to RGB node, a color ramp node, and then set the color stops to red and black. Then you can set up the lighting to shape the red and black areas of your model to whatever effect you're going for, either rim lighting or something else. You may want to turn off the shadows of your lighting to not have them interfere with the shading, and you can also use Fresnel or other shading possibilities like using height or depth-based gradients. You can also make a sharper mask by switching the ease interpolation to constant. And this was the exact couch we used in the lighting overview. Last, we wanted to cover some frequently asked questions, starting with how to paint mask maps. So I have a transparent layer here, and I could easily paint red, green, or blue, but it's a bit of an eyesore. We can't paint in the color channels unless there's some pixel data on the layer. So first I'm going to fill my layer black, and then bring the opacity down so I can see what I'm painting on. Then in the channels, I'll select the red channel, and then rather than the rim lighting for this, I'll paint a mysterious symbol in white. When I'm done, I'll bring up the opacity, export the image, and add the mask map to the rock in Unity. And yeah, this is a really cool, simple effect for magic, puzzles, or secrets. Let's take a look at creating a shader graph for lit sprites with an emission map. And as I said in the beginning of the video, this shader and the potion shader are available in the link below. For this, you'll want to have a volume with bloom. Let's go into the shader graph and look at some of the nodes. The 2D light texture node accesses these render textures that are created by the 2D renderer. Lit shaders sample these light textures to create the lighting effect on sprites. Here I've pressed play and we can see the light texture in the sample texture node. If we flip it with the 1- node, there are higher values for the shadows and lower values for the lit areas. That means that our emissive texture is influencing the shadowed areas much more than the lit areas. If we don't do this, I'll bypass things. The emission acts more on already lit areas, and our scene lights end up boosting our emission, which doesn't really make sense. Once we have the emission affecting shadowed areas, we add it to the light texture, and the main texture is multiplied with the result. I also have a sample texture 2D for the normal map, and on the node the type is normal, not default. If your secondary textures are set up in the sprite editor with the shader graph parameter names, then you don't need to expose them on the material in the shader. Finally, we have using mask textures for effects. In this case, the mask is being used to mask the potion inside the bottle. We can also light the inside of the bottle with the same mask, since it's probably the liquid that is glowy magic and not the glass bottle. This could be a UI element or an inventory item that changes as it's used, so there's a parameter exposed for the amount of liquid. Let's go over the graph quick, starting in the middle. Okay, so we have the regular textures, but we're also using a wave texture, which is this. So we're stretching this texture out on the X and then offsetting it every frame. The top of the potion is the same moving texture, but the offset is different both on the Y and X position. We'll look at that in a moment, but the real magic of this effect is using the spherize node into the UV input of the tiling and offset node, because it creates the illusion of volume inside the bottle and makes the wave mask look more organic and less like just a mask texture. Moving to the left now, we have a time node driving our wave texture X offset movement. There's a wave speed parameter, which I've divided by 20 to have better control over the values. Then we have a waterline offset for the X of the top wave. For the Y up and down, we have a remap node to convert 0 to 1 to precise Y positions on the bottle. And then the top wave, or potion waterline, has an extra offset above the bottom one. We're also bringing this time output into bubbles at the bottom. And here you can clearly see the spherize node warping the bubbles. Finally, we're putting down our potion color and masking in the top color with the top wave. We then mask in our bubbles, which could use some work honestly, but this is just to get you started. And then we use our bottle masked wavy liquid to blend the potion into the bottle. Alright, that's a wrap. Get these potions and the emission shader at the link below. Thanks so much for watching.